In this lesson we will build our first machine learning model. In particular, we will build a linear regressor. So this is the plan of all the methods we will see. We will just focus on linear regression today. So I will start by giving some generality on supervised learning model. Then I will define mathematically what is a linear regression, and we will play with this model. So we will see how to train it and then to validate it. We will extend it going to polynomial regression, and then we will examine one of the fundamental trade-offs in machine learning, that is model variance or complexity versus parsimony. In order to keep our model parsimonious, we will then explain some regularization techniques. And we will also see the importance of scaling the features before training a model, and how to select the most important feature of our dataset. So let's first start with supervised learning. So how do we learn after we are born? So we need a guide that is our parents, who tell us how the world works and what are the labels of each thing around us. So after we see a bunch of cats and our mother told us this is a cat and a bunch of dogs, then we learn what is a cat and a dog. It means that whenever a new sample comes, we are now able to infer its label, if it's a dog or if it's a cat. For machine learning algorithms, it's actually the same. So we first need, for supervised machine learning algorithms, it's actually the same. We first need a labeled dataset where there are examples already labeled of cats and dogs in this case. We give this dataset in input to the algorithm, and the algorithm at the end, with the mathematics that we will see, is able to infer the label of a new example that it didn't see before. So this process is called, so we first need a process of training, so ingesting labeled examples, and then we can do inference, also called prediction. Okay, there are many things we should discuss. For instance, that it's true that now machine learning algorithms, in particular deep learning algorithms, are better than humans to classify images, at least in the well-known datasets. But it's also true that in order to do so, they have to ingest millions of pictures, while humans just need few examples. So humans are more efficient learners than machines. Okay, so what does it mean learning? So I went to check a dictionary, and Cambridge English Dictionary says that it is the process of getting an understanding of something by studying it or by experience. And actually this experience in our case is ingesting labeled examples. In the context of communication networks, what can we learn? We can learn how to recognize anomalies or attacks. We can learn how to observe an encrypted traffic trace and understand what are the application protocols that are hidden in this trace. We can observe the same trace and learn what is the quality of experience that the users are observing. We can, by observing some monitoring data, we can infer if a certain device is going to break or not, etc. So let's just focus on one of these examples. That is the one that we've already seen in the first lesson in the code. So we have a dataset, and in this dataset there are connection information, like every 100 milliseconds we have how many packets were exchanged between an endpoint and the other, how many retransmissions, the throughput, so the amount of bytes exchanged per second, etc. but the traffic is encrypted. So we have like a set of bits and we don't understand what's inside these bits. Still, we want to be able to understand what is the video, if users are consuming videos, and in this case we want to understand what is the resolution that they are getting. This is of course important for network operators because they are interested in knowing if users are experiencing poor quality, but they can't do deep packet inspection. They can't look into the user's packets because the important information is encrypted. So what can we find in such a data set? So we have this kind of columns or feature. The mean throughput, the standard deviation of the throughput, the same thing for the packet size, the same statistics for the inter-arrival time between packets, etc. And our label is the resolution of the chunks. Okay, this is what we want to understand. And it's expressed in 300,000p, 720p, etc. In order to perform this inference, we would like to have a function that we call h, in which we give as input the features of a sample, and it is able to give us the label, which is the resolution that the user is consuming in that time window. Now, as I've already told you, if the label is a real number, our supervised learning model is called regression. If a label is discrete, this is called classification. So in our case, we have these resolutions as labels. So we could approach the problem as a classification problem because we have a discrete number of possible resolutions, but we have also the freedom to approach the problem as a regression problem because at the end of the day these resolutions are also numbers, even if they cannot take any value. And in this course, for simplicity, we will interpret the problem as a regression problem. Let's have a closer look to our data set. So you have a set of samples. Each sample is actually a vector, so this is the sample number 1, and each element is the value of each feature. Okay, and in our training dataset we also have already the labels. So we know that in this sample here the resolution was 475, etc. So how can we know already these labels? Well, there are basically two ways. Either you set up an experiment in the lab, so you established that your clients are going to download first resolutions 475, then resolution 720, etc. So you know these labels in advance. Another way is that you create a plugin and you contact some people in order to install this plugin in their browser and to authorize the plugin to get measurements about the resolution of the video chunks. And actually this is the approach of one of the speakers that will contribute to this course, and he will explain it later. Suppose you have in some way collected your data set with your labeled samples. What is really interesting is to, given a new sample that you've never seen before and for which you don't know the label, you want to guess this label, you want to infer it. The way we do it in machine learning is that first we construct a model based on the observations we know. And this model is nothing else than a function, this h here, which takes as input your samples, the features of your samples, this x, and gives in output the label the approximation of the label. And you can compute this function for the training data sets and also for the test, for the new samples that you have. So when you compute the function on the training set, you can immediately compare if the inference is far or close to the true label that you know. So for instance, if someone gives you two models, you can immediately, for example, this model here and this other model here, by observing the distance between the inferences and the true label, we can immediately understand which of the two models is better. Okay, the closer the model is to the true labels, the better. And so even if we don't know anything about the new samples, we can intuitively understand that the first model, which is this one, that we can trust more the first model because it gave better approximations in the training dataset, so it is very likely that its approximations are also good for the new samples. So the central part of a machine learning algorithm is to construct this approximation function h that is called model. So models have been constructed all along the history. These are just some examples of famous models. For instance, if we take the Newton law, we see that it is nothing else than a model with two parameters, with two features, let's say. If you have the mass and the acceleration, this model tells what is the force, which in this case is the label. But these scientists arrived to formulate a model thanks to their intuition, their ability to observe, and their reasoning. To do so, we have first to decide what is the structure of our model. For instance, if we decide to have a linear model, this is the structure we are choosing. So the approximation function in this case is just a scalar product of our vector of features of sample I multiplied by the vector of parameters. So we have one parameter per each feature. For instance, if our features are the mean of the throughput and the standard deviation of the throughput, this is what we have. Okay, so we give as input any sample xi, and we have as output an inference, in this case is a resolution. This is just one of the possible structures we can have. Another example is the quadratic model that is a bit more complicated, and we will see it later. It has not only one parameter per each feature, like this, but it also has one parameter for the squared of the features, etc. We will see it later. And then we have even more complex functions that we can choose. For example, the ones that are resulting from a neural network that we will see later. But in any case, observe that we gave a structure to the functions, and now training means just to find the right parameter theta in order to minimize the error. So if the error is the difference between the actual label and the inferred label by our model, the error, also called residual, is just the difference, is this one. We define a loss function, which in this case is this function here. We will see there can be different loss function, and what we want is to minimize this loss function, which is summed over all the samples. So training means to solve this optimization problem. Okay, so after we expressed our learning problem into an optimization problem, we can use algorithms available to solve this. And we can resort to matrix multiplication, we will see how, or gradient descent, or other techniques. So, let's give a simple example of a univariate model in which the only feature is this one. We have one feature, kilobytes received, and okay, the label is always the resolution of the video. Now, what does it mean to have a linear model in this case? It means actually to trace a line like this, whose equation is h x, given any sample xi, the equation is some theta 0, some offset, plus this coefficient here, theta 1, multiplied by the feature kilobytes received. Okay, so we are now constructing a model like by hand, visually, okay? And this is our approximation function. Of course, and why it is important to construct a model? Because like this we are generalizing. What does it mean? That we have first observed the samples for which we know the resolution, but then we generalize by constructing a general function like the one that I wrote, so that if a new sample comes, let's say it has kilobytes received 500, we can immediately infer the resolution, that in this case will be around 600. So building models allows us to generalize. Instead of building models manually, we can instead let a machine learning algorithm calculate it for us. For instance, in this case, I run a method called ordinary least square regression, which minimizes the loss function, so the error between the true and the predicted labels, meaning that it finds the optimal parameter theta. So when I run this on the dataset that I shown in Python, I obtain these two values of the parameters. So if I replace them here in the equation, I obtain a model which I know for sure minimizes the loss function in the training dataset. If we are in 2 dimensions, we talk about a bivariate linear model, and our equation h actually gives us a plane. Okay, if we are in more than 2 dimensions, our linear model gives us hyperplanes in general. So before we go on, let's spend 1 minute on the notation. So we can indicate the entire dataset as a matrix X, where each row is a sample. And so if we look at the first row, we have all the feature values of the sample 1. So from feature 1 up to feature n. And note that we also add every time a 1. Okay, so this first row is equal to the sample vector xi. Okay. Then we also have the vector of the true labels and the vector of the model parameters. Notice that we have one parameter per each feature. Okay, so if you have n features, this is what you get. And we also have an additional parameter, theta 0, that is called bias. So when we multiply actually the vector of parameters by the vector of features of a sample I, we have theta 0 multiplied by 1 because we added the 1, plus the sum from feature 1 to feature n of theta j multiplied by the j feature of sample I. And finally, we have the vector of predicted labels, this one, which is actually the result of our model for each element of the dataset. Okay, and so we indicate the fact that it's an approximation of the true labels by using this hat symbol. So if you want to understand the quality of your model, you just compare this vector with the vector of the true labels. When I say compare, it means you compute a function that we've already encountered called loss function. There are different types of loss functions. The most common in regression is the mean square error, because you compute the residual, so the difference between the prediction of each the training sample and the true label. You square it like this, you give the same weight to the positive and the negative errors, and you compute the average over all the m samples. If you want, you can also compute the root mean square error, that is just the square root of the mean square error. And you can have other kind of loss functions. When we will see classification, we will employ completely different loss functions. But at the end of the day, whatever loss function we have, a machine learning model aims to solve these optimization problem. Finding the parameter, given a certain structure, a certain parametric model, find the parameters which minimize the loss function. Note that the loss function depends on the data we have. Okay, so if your observed samples are different, you will end up with another result of the optimization. So you will end up with another optimization model. So this is why the models depend a lot from the training dataset that you use to build these models. Ordinary least squares is a way of training a linear model in a very efficient way and simple way. So we know already what is a linear model, okay? We have seen it. So in ordinary least squares, we choose the mean square error as our loss function. And it can be shown that the optimal parameter vector, that is the one that minimizes the loss function, is simply given by this matrix multiplication, where again x is the matrix of our dataset, the feature matrix, and the y is the vector of the true labels of our dataset. So observe that this result makes computing a linear model very efficient and very fast. You just have a dataset with the x and the y, and you apply this matrix multiplication, and you immediately obtain the parameter vector, so that you can replace this parameter in the equation of the linear regression, and you can then compute all the inferences you want. Observe that there is a detail here. This equation works only if x transpose multiplied times x is invertible. Okay, you may ask, what can happen when this is not true? But we will see it later. Okay, here in these slides that are in gray, I put the proof of this theorem here. But all the slides that are in gray will be skipped in these lessons because they are outside of the course this year. So you can ignore all the gray slides. In this slide I run ordinary least square for a multivariate regression model. Multivariate because I'm using different features. The result looks something like that, where the first number is the theta 0, the bias. The second number is theta 1, etc., etc. So let's interpret this model. So what this coefficient is telling us is that whenever in our observation window, that is 100 milliseconds, whenever the user receives 1 kilobyte more, then its resolution is likely to increase on average by 0.60p. Okay, so, and you can understand it makes sense. The more kilobytes we received, the better. Let's check instead this coefficient. Does it make sense? Well, this coefficient is telling us that this is the coefficient for packet sent. So it is telling us that the less packets the user has sent, the better the resolution he has. And of course, it doesn't make so much sense. What I'm telling you is that whenever you run a model and you get the result, the algorithm is just trying to minimize this loss function and to run an optimization problem. And so at the end of the process, you may end up with something that doesn't make sense at all, and it is only adapted to your data. We will see how to fix this, but I already warn you that you shouldn't use a model like that. Another information that you can use is the p-value. Unfortunately, we will not have time to explain it, but the less the p-value, the more you can trust the coefficient you get. In this case, the p-value is very high. An acceptable value of p-value is 0.05 or less. Okay, this is just a rough guideline. Unfortunately, we will not have time to cover the p-value. Imagine you have obtained your model via ordinary least squares or any other method. Now you want to understand if your model is good or not. In other words, you want to validate your model. So let's see how to do it properly. As we've already seen, we constructed our model, we trained our model based on the observations we know exactly, for which we know the samples. But the final goal is to be good at inferring the label of the new samples. Okay? So it's like when you're preparing an exam. You first train on exercises for which you know the solution. But then the important thing is to be good during the test for exercises of which you don't know the solution yet. So what you want to do when learning is to generalize the knowledge you acquired on a well-known dataset to any general situation, any general instance. To be sure that your model is able to generalize, this is what you should do. Okay, you are given a dataset with your features and your true label, and each row is a sample. Okay, so you should first divide the dataset in two parts: the training dataset and the test dataset. You forget about the test dataset and you put it aside, and you just train your model on the training set, trying to, aiming at minimizing the loss function on the training set. At the end, you obtain a model, okay, the optimal parameters, and thus a model. And then you compute a posteriori the loss function of that model that you found on the test set. This error here is called test error or generalization error. And this is the actual measure that indicates the quality of your model. What is the right way of dividing training and test set? Well, the first thing you could do is to divide it just in two parts. You take the first samples as the training set and the remaining ones as the test set. But this is dangerous because maybe the person who gave you the data set performed first all the experiments with low resolutions and then the experiments with high resolution. So in your training data set you would build your model only on the low resolutions, which is not representative of all the situations. So to be safe, it is instead better to randomly choose the training samples and the test samples. Let's now write our first linear regression model in Python. If you go to my GitHub account, you go to regression and then a.regression. And this is the notebook you can use to run your linear model. Let's open it in Colab. Okay, so at the beginning, of course, we always import libraries. Okay, and here we have standard libraries and also some libraries that I prepared for you, which is Andrea models. Maybe I'll zoom more. Andrea models. Okay, and feature engineering that we download directly from my GitHub account. Okay, so you just copy and paste this code and you can use this model, this library that I prepared. Okay, we can skip this because we are not going to save figures, so you can ignore. So first, let's download the data sets. So I first need to define the data set. This is this one, file name, and to download the dataset. Okay, we downloaded the dataset that is called df.a2csv, and then we can download it. We can load it in a data frame. We can check it as we did last time. We can view some information about the columns, etc. Let's first plot the kilobytes received versus the label. Okay, this is what we get. You can skip this. We will see how to save files into Google Drive in another notebook, the next one. So, as I told you, the first thing we should do is to divide training and test set and to put the test set aside. And this is what we are going to do. So, we use this function, train test split. We give the entire data set and it gives you two data sets, the training and the test set. We are saying here that we want 30% of test set, so 70% for training. And here I'm visualizing the test set. If we observe this number, for example, the first sample of the test set has packet sent 22. If we do it again, we have 11. So it means that by default in train test split, first the dataset is shuffled, meaning that the samples are randomly changed their order. So every time we run this function, we get a test set that is different. If we want to be sure that every time that we run the function we always have the same training and test dataset, we have to establish a so-called seed by using this random state equal to whatever number. So if you run the same function with the same number here, you will always obtain the same test and training dataset. This can be useful sometimes if you want to debug your model and so you observe the problem and you want to reproduce the problem. Okay, so let's now focus on the training set. Let's forget about the test set and let's see what are the samples here. Kilobytes received and label num. So here we are using kilobytes received as the only feature. We are doing here univariate linear regression, and label num as the label, the target feature. This is what we want to learn to infer. So before building the model, we have to do some pre-processing. So we need to isolate the feature matrix just by considering our features, kilobytes received in this case, and we call it xtrain. We have to do some pre-processing necessary in scikit-learn. Here I explain why it is needed, but it is not conceptually important. And we also separate from the training set the target, the label. Okay, and we call it yTrain. This is an array. And we do the same for the test sets. So we have the feature matrix for the test set and the label vector for the test set. Now we can train our model. So let's first run this code. Now let's train our model. Observe here that first we are creating the object model and then we are fitting it. Fit is a synonymous of training, it's the same thing. So, and observe that we are training it just by giving the features of the training set and also the labels, the examples. And we are specifying that the model has to only consider kilobytes received as the only feature. Here we are summarizing the model that we obtained after training. So I don't have time to explain all these numbers. The only thing you can understand is these coefficients that correspond to the theta 0 or bias and the theta 1, the coefficient of kilobytes received. Another value that you can observe is the p-value, which, as I told you, the lower the better. We will not have time to explain the meaning, but the lower the better. If you want to trust your coefficients, you should have a p-value that is 0.05 or less in general. So now we have this model that is within this object here, and we now want to use to make inference of new samples. So in this line I'm inventing random samples, and I'm inventing some samples. So these are the values of kilobytes received, and now with this line I'm predicting it, the label of these samples that I invented, and these are the predicted labels. Okay, 893, 1281, etc. We can also plot this model. The simplest thing to do is to create a set of samples that go from minus 100 or 0 if you want to 1200, sample space by just one unity, and we can predict each single sample of it. So we obtain all the labels for all the samples with kilobytes received minus 100, minus 99, minus 98, up to 1200. And now we can plot. Here I'm plotting the training data set. So here actually I'm reusing the plot that I showed you at the beginning, okay, which was, if you remember, with the red dots, and now I'm coloring in blue just the training samples. Okay, so the red ones are the test samples that we are not using to train our model. We are just using the blue samples to train our model, and I'm plotting it. And I'm also plotting the predicted labels of the numbers minus 100, minus 99, minus 98, etc. Okay. Now this is just for plotting our model, which is a linear model, so it corresponds to a line. Now let's predict the labels of our test set. It is simple as it is this. And now we can compare the true values of the resolution of the test set, that is y test, and the predicted values that are in y pred. And you see that there's of course a difference between our predicted value and the true value, but we are not so far in many instances. And we can compute the loss function on the test set, the mean square error in this case. And this is this number. Of course, it is not easy to evaluate the mean square error because it's squared. So it has not the same magnitude of the actual resolution. So it is sometimes easier to compute instead the root mean square error. So here it is clear that in the test set, on average, we are making an error of 273p. Now, I want to show you that if we now divide the training set and the test set in a different way, so here I'm using another seed, we obtain other two subsets, and if we now train our model on this other training set, we obtain a different model. You see this orange line is a bit different from the model that we trained before. This is just to show you how our models depend strictly on the dataset they are trained on. Let's do it again with another training set, and we obtain this green line, okay, which is completely different from the other models we got before. So now we have observed in the last lesson that sometimes it is beneficial to transform features, okay, and logarithmic transformation is very useful when the values of our features are squashed into just the low numbers. So if you want to zoom in the low numbers, we use the logarithmic features. So let's try now to train a model on the transformed feature instead of the original one. So kilobytes received log. So first let's plot a scatter plot, and let's now train the model. Here we just replace kilobytes received with kilobytes received log, okay, to create our X train and also X test. We train it, and let's plot our new model. And now let's predict the resolution on the test set, and let's check the root mean square error on the test set. This is the result. So this is a bit lower than before. So you see, training a model on the transformed test set with the logarithmic transformation has improved the accuracy of our model. And this is the new model with the new coefficients. Now, so far we have used just one feature. Let's now try to use many features, so to make a multivariate regression. The first question that comes into our mind is, which features should we choose? One guideline could be, for example, to take the most correlated features and to try to use them into our model. So let's take the most correlated features to label num, as we did last time, and these are the ones. Okay, for example, start time is very negatively correlated to label num. Sorry. So now let's train our model with these two features, kilobytes received log that we used already, and additionally start time. The code is the same, just that we specify that column names is calls, these two, instead of just kilobytes received. And also, a very important, the X train is the data frame from which we just extract calls. Okay, these are the new coefficients. So we have the intercept and the coefficients of the two features. And now let's extract the feature matrix for the test set and predict the resolution on the test set. And let's compute the new root mean square error, the new loss function. You see that we improved a bit with respect to before, that we just used one variable. Okay, the improvement is like negligible, it's very low. But anyways, we might be tempted to use the second model, multivariate model, because the error is lower. However, pay attention, because the other column we are using is start time. That is just the time, the clock time at which that connection started. This is not an important feature. This has no relation at all in reality with the resolution. Okay, this may a negative correlation with label num in our dataset may be just due to the fact that the experimented focus more at the beginning of the measurements on the low resolutions, for example, and then it started the experiments with the higher resolution. So if we use the start time, we may risk to have a model that is very well adapted to our training dataset, but then in real life it will just not work properly. So don't be obsessed by reducing the error and take whatever feature you have to reduce the error. You have always to be critical and to understand which features really make sense and which not. So let's now use other features that intuitively make more sense. And let's fit again the model. Okay. This is what we obtain. This is incorrect, sorry. Okay. This is what we obtain. So it's we improved the model a bit. So it's good to consider these three features: packet sent, kilobytes received long, packets received log. Suppose now we take all the numeric features, all these ones. Okay, here I'm selecting the columns that are numeric, all. And they are 140. Okay, let's just drop from this column, of course, the label num, because this is not a feature, this is the label we want to be able to infer. The start time and the epoch time, because as I explained, it doesn't make sense to consider them. And let's train the model on these 140 more or less features. First, observe that there are some warnings. We will explain what it means later. Let's run the model, and wow, the error now is very high. So we considered more features and we are getting a worse model. So we will now understand, coming back to the slides, why it is happening. But this is already something you have to think about. It's not true that the more data you get into your model, the better is your model. Sometimes it is, on the contrary, better to be parsimonious and just to take the right features, which is not an easy task, and we will understand how to do it properly in this lesson. Let's try to understand why, even if we ended up with a very rich model with a lot of features, the error was very bad in the test set, way worse than when we had just one single feature. The cause is that the model is unstable, and let's try to understand why little by little. First, consider this data set here, where we have a column that is a constant. It doesn't change at all. So in other words, the variance is actually 0. This means that this feature matrix has no full rank. And if you try to compute the inverse that is needed for the ordinary least square equation to compute the optimal parameters, you cannot compute the inverse. And so, actually, you can compute the inverse, but this is not unique. So, in other words, ordinary least square cannot work properly. So, the first check you have to do is to eliminate the columns with 0 variance in order to make ordinary least square work properly. The second thing to verify is that there is no collinearity between features. So a feature J1 is collinear with J2 if the two columns are proportional. So if you have a feature matrix like this, again your matrix has not full rank, and again this matrix here in the ordinary least square equation cannot be computed because the inverse doesn't exist. And this is another case in which ordinary least square will not work. So before, you should eliminate columns like bytes received and kilobytes received that are one proportional to the other. In reality, we may have quasi-collinearity, meaning that one column is quasi-proportional to the other. So let's then write a generic linear model and suppose that J1, feature J1 is quasi-collinear with feature J2. So we can rewrite the equation in this way, collecting xj2. Now, suppose alpha is equal to 2, and suppose our model has theta J1 equal to 1 and theta J2 equal to 3. So inside these brackets, the coefficient is 2 plus 3, 5. Okay. So now observe that this model is exactly equivalent to this other that I'm writing here, in which theta J1 is equal to, for example, 200, and theta J2 is equal to minus 395. Because if you replace these values inside the brackets, you will see that at the end you have the same result, that is 5. So I'm showing you that in case of quasi-collinearity, I'm creating two models that are completely different, but if you apply them in the dataset you have almost the same result. So when you compute ordinary least square on a dataset like this, your algorithm may choose the first model or the second model almost in an equivalent way. So if it suffices that you vary a bit, a small epsilon, your dataset, that then ordinary least square will choose the other model instead of the first. Okay, so this is an example of an unstable model. That is the one in which you change a bit the dataset on which you train it, and the model changes completely its coefficients. These models, of course, are not good. Okay, there can also be the case of multicollinearity, meaning that one feature is a linear combination of other features. This is more difficult to discover. At the end, you have the same problem. So it means that your matrix has not full rank, and so when you compute the inverse of this matrix, you will have an unstable result. So again, multicollinearity, you should avoid it, and to do so you have to eliminate the columns in order to prevent multicollinearity to appear. You will see, and I will show you in the code, that if there is multicollinearity, the code will raise a warning, so you will understand it. So let's try to recap about this aspect. So we understood that when we have multicollinearity problems, or all quasi-multicollinearity problems, our model is unstable. We can also say that the model suffers high variance. This happens whenever, even if you change a bit your training dataset, the model changes completely. So here I'm writing you the thing in equations, if you like equations more than words, like me. So here I'm taking the dataset, let's say one dataset, any dataset x, y, and I'm supposing I perturb a bit the values of x and y. Okay, and if I train the model on the perturbed dataset, of course I obtain a different set of parameters. Now, if a model suffers high variance, the set of parameters that I obtain with the two slightly different datasets is completely different. Okay, so such a model with high variance is very bad because it's not able to generalize. Actually, it is just suffering from small deviations, and this is not how learning should be. Here I'm adding an example in real life. So suppose that when you're a child, you learn to distinguish dog and cats. So if you train on this dataset, actually at the end you will learn the same thing as if you were trained on this other dataset here, where you have small differences. Here you have a cat with the hat, while in the first dataset you don't have, and you have the dog with the collar, while here you don't have. So humans will not be misled by these small details. Humans are robust, are stable learners. They learn really the core, the meaning of things, instead of being too adapted to the small details. So learning is a process in which you have to forget about details, you have to be approximate and to learn in a gross way, let's say. So when we run a machine learning algorithm, we try to imitate humans. So we want to avoid high variance models. And the case of multicollinearity is an example of high variance models. We will also see along this course other examples of high variance models. Let's go back to our model and let's try if we manage to improve it by using the theory that we have just seen. So here we will use this library that I created for you that is called feature engineering. From this library, here you see the docs that I created. From this library, we will use this function, which just returns the features whose variance is above 0. That means all the features that are not constant. And let's train a model with this just these features. So we are eliminating the constant features that create problems, as we've seen in the theory. And if we compute again the test error, we see that we improved a lot with respect to before, where we also had constant features. Okay, but yet this error is way worse than the univariate model where we had just one feature. So how can we improve again the model? So let's check if there are collinear features. And here I'm computing the covariance of pairs of features. This is another function that I created for you that gives the most correlated features between them. So you see that these packets received 12 and bytes received 12 are perfectly correlated. It means that they are actually perfectly collinear. They are actually, let's say, they give the same information. When one increases, the other always increase by the same quantity, and so there is no interest in keeping the two. On the contrary, they create collinearity, which impedes to have a correct inverse matrix when we compute ordinary least square. So here I'm just removing from these pairs of features one of the two in order to avoid pairs of collinear features. And let's see if we improve. Yes, we improve. Okay, we have improved a lot our error on the test set. Still, we are worse than the univariate model. So we are going better, but we are not there yet. The fact is that even if our model is better than before, still it is saying, the library it is saying that this might indicate that there are strong multicollinearity problems. So still maybe we have too many features and one may be a linear combination of the others. So let's try to look again for other collinearity problems. Yet there are some features that are very highly covariant or correlated, and so it may be good, instead of taking them all, just to take a subset, actually the subset of features that is the most correlated to the to our target. So here I'm just selecting some of the columns, okay, some of the features. Let's try again. And here we are going worse. Okay, so let's see, try to remove even more features. So I'm removing all of these, and let's compute again. Okay, here. So finally we have an error that is better than the univariate model. Okay, so let's see what are the columns that we are considering now. So let's add this. Okay, so out of 100 something columns, we are now considering only these columns here. So you see that we started with the small model first, the simplest one. That was a good starting point because it was already not so bad in terms of test error. Then we tried to improve, but we understood that when we added too many features, we were going worse. So then we started to remove features up to the point in which we finally have a multivariate model that is better than the univariate model. So you see that finding a good model is a matter of trial and errors, and but it's also a matter of understanding what's going on with your data, if there's collinearity or quasi-collinearity or multicollinearity. We have seen that due to collinearity problems, our model may suffer high variance, so it can be very unstable. So how can we check this? The best way to do it is cross-validation. What does it mean? So we have so far divided our entire dataset in training set and test set, and we have trained the model on the training set and measure its performance on the test set. But are we sure that the performance that we observe are general trends, or are they just due to the way we are splitting training and test set? So we can't be sure. This is why, in general, it is good practice to implement cross-validation. It means that you divide your data set in a training set and a test set. You do what you have done so far, train on the training set, measure the error on the test set, and you put this measure aside. Then you divide again the entire data set in another training set and test set, and you repeat the same observation. And you compute at the end the measure, the performance on the accuracy on the test set, and you put this number aside. And you do it many times, k times, and at the end you give a final error, that is the average of the errors that you've observed all the times. So this method is called k-fold validation, and k can be 5, can be 10, it depends from what you want. So usually what one does is that you divide, let's say you are doing k-fold validation, so you divide your data set in slices that are of equal size normally, and then you say, okay, now the last part is the test set and the rest is the training set, and you measure the performance. Then you say, now the test set is the first one and all the rest is the training set, and you do the same. Then you say, okay, the test set is the second one and all the rest is the training set. And you repeat this until all of the slices have been a test set. So to do this in code, it's not worth doing it manually. It's there is a code that does it for you. Let's see it. Okay, here. So let's start with the model with the features that we constructed so far. Okay, with like almost 10 features and so on. So to run k-fold validation, we just have to use this function in which we say divide the dataset in 5 slices, and this is just a seed to always have the same divisions, the same partition of the dataset. So you obtain this variable k-fold, and then you use this function cross validation score, in which you give the model you want to run. You say cross validation equal to this partition that you decided, and then you decide a score function. Score is the contrary of error, so we choose a score function, the negative mean square error. So if you compute this, it will run training and test 5 times. At the end you will have the scores of every one of these 5 times. And of course the actual mean square error is the negative of the scores. And this is it. And then what's important is to compute the mean. As usual, mean square error is difficult to understand because the magnitude is different from the one of the label, so it's better to compute the square root of the mean square error. So here we understand that on average our test error is, or also called cross validation error, is 490p. So this is the cross validation error with the set of features that we have chosen so far. Let's check again the very simple model with just one feature. If we repeat again the cross validation with this model, we obtain a cross validation error that is 278p. What is it telling us? That the univariate model is actually better than the one with many features. So on the initial training test split that we've used, the model with the many features seemed to work better, but it was just an impression. It was just due to the actual training and test set we were using. If we instead use cross validation, we can understand that actually the univariate model is the best. So again, this is to show you that the simpler the model, the better. That's all for this lesson. This is what we have done. We have introduced supervised learning, and we wrote our first supervised learning model. In particular, it was a linear regressor based on ordinary least squares. We wrote it in Python. We also understood the theory behind it. Then we did some feature selection, because we understood that we have to choose the right features and not include in our model as many features as we have. And we also introduced some techniques to validate the model. First, the simplest one, that is dividing the dataset in training and test set and just evaluate the error on the test set. And a more complex one, but more reliable, that is cross-validation. In next lesson, we first will continue on regression. We will extend linear regression to polynomial regression, and we will see in this context what is the trade-off between having a model that is very complex or more parsimonious. We will understand that it's better to not to complexify too much our model, and in order to keep it simple enough, we will introduce regularization techniques. We will also see why scaling is important and other feature selection techniques. Then we will start with classification, and we will start with the simplest method in classification, that is logistic regression. We will see what are the metrics to judge classification and how to deal with the problem that is very frequent when you do classification, that is class imbalance.